So this is the geodesic equation, clear? Now let's forget it this equation for the time being. When we wrote the equation of a free particle, okay, so what was the geodesic? Okay, what was the equation for a free particle? Like this thing. If you remember, dui by d tau, that's equal to 0 because it moves with a uniform velocity in the which space time? In the flat space time. We had this kind of equation describing what? An equation of motion for a free particle, or you can say it's a geodesic equation for a free particle in flat space time. Clear? Now then we argued that this equation is not actually invariant under a general coordinate transformation. So in one frame of, okay, so in under flat space time transformations, this equation is an invariant quantity. This equation will hold in any frame of flat space time references, clear? But if we make any arbitrary kind of transformation, any general coordinate transformation, this will not be invariant, okay? Then we generalized this equation to any arbitrary space time to this geodesic equation, clear? Just for the reason that we need an invariant equation, okay, that holds in all frames of reference. Now let us look at this very equation carefully. So this is the part dui by dt, is it? So if I am saying this is an invariant equation under any general coordinate transformation, that means in one frame of reference you are having this equation, in another frame of reference you are having the same equation, okay? It will be the same everywhere in all frames of reference. Now the point is that you are having this dui by dt, is it? So this itself does not transform, okay, or in other words, this is not an invariant quantity. Yesterday we saw this gamma I jk, this is also not an invariant quantity, or either, in other words, this does not transform as a tensor, clear? Have we seen it? This also does not transform as a tensor, dui by dt, under a general coordinate transform. It means under a general coordinate transform, some of these two terms has to transform as a tensor. So we can treat this entire equation as a tensorial equation. Okay, so let me rewrite this equation in this very fashion. Okay, so I can write this as dui by d tau like this thing, dxa by d tau, okay, then I can write dui by, okay, by simply chain rule like this thing. Can I write it? Okay. So what this object is, can anyone tell me? So this is simply ua, this I can write partial a ui. Can I write it? Okay, good. So then I can recast this equation in this very fashion. So let us rewrite equation first. So this equation implies ua partial a ui plus partial I, okay, jk. So let me write, since k is a dummy variable, j is a dummy variable, clear? So let me write it as something, okay, so let us write aj, or you can write j, ja uj ua is equal to 0. Can I write it? Because k and j both are dummy variables, you can replace it by any index, so that I can take this ua common, so I can take the velocity, this u from both the terms common, okay, so I can write it like this. So partial a ui plus partial I ja uj, okay, so that's equal to 0. Samajh clear? So now let's check whether this quantity, so now let's check, so what this u is, it's a 4 vector, so that means this should also transform as a 4 vector. Samajh, or in other words, this should transform as a tensor. So how many indices you are having here? How many free indices you are having? Forget about this ua for the time being, forget about this ua. How many indices you are having here? 2 free indices, clear? So that means this should transform as a tensor. So if it transforms as a tensor, that means my equation of motion is invariant under a general coordinate transformation. That is why we require tensors for describing physics. because tensor is something, it retains its property in any frame of reference. समझ आवा? तो यहाँ क्या समझ? So as an individual term, this does not transform as a tensor, and this gamma also does not transform as a tensor. Now let's check whether this total quantity transforms as a tensor or not. If it transforms as a tensor, that means this product, okay, transforms as a tensor. समझ आवा? चाहिए समझ? हक़ से नहीं समझ. तो वो सुकून वो बहुत सिंपल है. dui by d tau is equal to 0. So this is a free particle, okay, in flat space time. Clear? Space time. So this dui by dt I can write as ua partial a ui is equal to 0. Can I write it? समझ? Okay. Now this ua is a 4 vector. Forget about this object. This ua is a 4 vector. It means, so if this has to hold in any frame of reference, that means this equation should be same in any frame of reference. Okay? If I am saying if this equation is an invariant quantity, it means the transformation property of this, this equation, in other words, this equation should hold in any frame of reference. But in flat space time, it's okay, because flat space time transformations are linear transformation, Lorentz transformation I mean to say. Under Lorentz transformation, forget about this ua, this transforms as a tensor, because how many indices it is having? 2 indices, it means it transforms as a tensor. Clear? So in other words, this product, since a will be now contracted, how many free indices you are having? 1 index. So under Lorentz transformation, it transforms as a vector. So when it transforms as a vector, it will retain its property, okay, in any frame of reference. I mean in any frame of reference defined in flat space time geometry. Clear? Or in other words, you will be, this form of equation will remain same in any frame of reference. Clear? Okay. So now let's look at this thing. Okay, now let's look at the curved space time. Okay. So under curved space time, so if I take now curved space time, so this partial a ui, it does not transform as a tensor. Okay. So this we have seen, this derivative is not a tensor. Clear? So if it is not a tensor, the product of this ua and this object, it will not be a vector now, because you are having only 1 index, so it should be a vector, but it's not now a vector under a general coordinate transformation. It means when it's not a vector under a general coordinate transformation, this equation does not hold in any frame of reference. Okay? So that means the form of the equation will change. समझ आओ? Now let's okay, for that matter, what we have done for any general coordinate transformation or any curved space, we have defined an equation of motion for a free particle like this thing, okay, which we call a geodesic equation. I am saying this equation retains its form in any frame of reference, or this equation is an invariant quantity, or it is invariant under general coordinate transformation. समझ आओ? So for that matter, let's check. Let me rewrite it in this fashion. So I have written it in this fashion. So I am saying ua is a vector under general coordinate transformation. Clear? So forget ua for the time being. How many free indices you are having here? 2. The same way you are having there 2 indices. It means this must transform as what? As a tensor under general coordinate transformation. Clear? So that this product will transform as a vector, because you are having only 1 free index. Clear? For that matter, we need to check. Now let's check it individually. Look at this very term. What this term is? It is the same term, partial a ui, which we say it does not transform as a vector or a tensor, is it? And this we also am saying what? Yesterday, in the last lecture, we have said this does not transform as a tensor. So individually, these 2 terms does not transform as a tensor. Now I need to look at the sum, whether this sum transforms as a tensor or not. If this transforms as a tensor, that means this equation is valid in any arbitrary frame of reference. समझ आओ? Okay, so let's check it. So let's check it. This sum is actually a tensor. Okay. So in the primed frame of reference, okay, so let me write. So you are having in the primed frame of reference this object u prime I plus gamma prime I j a, let me write u j prime. Okay, so let's check this very object. Samajh aaya? Okay. So now how this transforms under, okay, so we have derived the transformation rule of this very quantity, is it? So first there are actually two terms, is it? You remember it? There are two terms corresponding to this thing. What are those two terms? First is the simple transformation rule. Okay, can anyone tell me? Partial x by partial x prime a, let me write a, then I will write partial x prime, let's say I, by some partial x, let's write here. Then you are having this partial c d c d. Okay, then you are having another term. Anybody, can anyone tell me? There is one more term. So what is that term? I forgot. So what is that term? Can anyone tell me? So there is a double derivative term. Clear? Okay. So you are having the same two terms. Okay, like this thing. Partial xc. Okay, so let me write partial x by partial x prime a. Then I am having double derivative of this x prime, this primed coordinate with respect to, let's say, okay, so let me write it partial x and partial x. Okay, so let's put it as a c c d. Okay, then you are having what, this object u. So let's write it as a d. Clear? So these are the two terms which correspond to the transformation rule of this quantity. This we have already derived. Okay. So now what is the transformation rule of this object? Yesterday we derived. So write the transformation rule as usual. It is as at the tensorial transformation. Then subtract a term. Clear? So what is that? So it is partial x prime I by partial x. Then you are having partial x by partial x prime j. Okay. Then partial x by partial x prime a. Okay, then let me write here this gamma. Okay, so let's write here c. So let me put c here. Then let's write d. Okay, so you will write d here. Let's write e. You write e here. Clear? Samajh aaya? Okay. Then you are having a. You need to subtract a term. Can you tell me? So because there is a this u prime also multiply. Can you tell me what is the subtraction term? Anybody? The same thing? Anybody? So you are having the transformation rule for this j and I, then the double derivative of this thing, like this thing. Okay, so let me write partial x by partial x prime j, then partial x by partial x prime a. Clear? So these two indices. Okay, then you are having a double derivative of this primed index like this thing, partial x kind of thing. Okay, so let's write it as d e d e. Okay, clear? So this is the term, and what is multiplying? So both the terms are being multiplied by this u prime j. What is that equal to? U prime j. So it is partial x prime j by some partial x prime a, b, c, d. Let's write c. Have we read? Okay, c we have already carried. Let's write u f. Okay. Samajh aaya? Everybody got it? So this is okay. So these two terms are the transformation rule of this gamma prime. Then you are having this u prime j. U prime j, you write it. Okay. So if anybody has still not understood how I have written these things, okay, if you are having a upper index, for an upper index you write a prime on the upper side. Clear? Don't write, you write a partial x. Okay. Then if you are having a lower index, put the what? X prime on the bottom, the lower index on the bottom, let's say x prime and x prime a. Then write the quantity what you are having here. Clear? So then adjust the axis on the axis where you don't have the indices. Those indices need to be adjusted where? On this gamma. So you need an index, an upper index and two lower indices. So this upper index will get contracted with this lower index, and these two upper indexes will contracted here. Samajh? This is a rule. So this is the first term. Second term, how you remember it? So write the transformation rule of the two lower indices, clear? And the double derivative of this index. Samajh? Got it? Similarly here, you are having a and I, upper index x prime, the same transformation rule. Then the next term will be, okay, the lower index as usual and the double derivative of the upper index, clear? So you are having a double derivative of the upper index. Samajh aaya? So this is a way to remember these things, okay? So now let's look at these two. Let's look at this very term. Okay. So let's look first at this very term. So these two terms. So what you are having here? So let me write this as 1. So this 1 is equal to, so let me write it, partial x d by partial x prime j, partial x e by partial x prime a, then partial to x prime I by partial x d partial x e. Then you are having this partial x prime j by partial x f u f. Clear? Samajh aaya? Now let's say there is a sum over j. J index is here and j index is here. Look here, in this very equation there is a sum over j, is it? So that means this very term, when you sum over j, these two, okay? So it means this x prime j, it cancels. You are having partial x d by partial x f. So these two terms give me what? Delta df. Clear? Samajh aaya? Now let's look at whether there is a d. Now you are having d as well here. So d index will come here, is it? So this delta function will be multiplying this entire expression. Now this will be non-zero only when d is equal to f. Samajh aaya? So in other words, I can write it, or f is equal to d. I can write it like this thing: partial x e by partial x prime a, partial to x prime I by partial x d partial x e. So u d. Can I write it? Can I write it? Can I write it? Okay. So this I can write as, since e is a dummy variable. Is e a dummy variable? Huh? So e and e are same, so I can write it like this thing: partial x c by partial x prime a, partial to x prime I by partial x d partial x c u d. Can I write it? Can I write it? Huh? Okay. So if I can write it, now look here, this very term is a positive term and this has a what? A negative sign. Samajh aaya? So that means this term cancels with this term. Okay? Clear? Any problem? Okay? How samajh? So you are having these two additional terms cancelling. Now let's look at this very term. Okay, this term, and it is multiplying. So let's call this as a second term. So it is means including that partial x f. Huh? So let me take the second term. Everybody has got it? Okay, good. So let's write this thing, second term. So that's equal to partial x prime I by partial x c, partial x d by partial x prime j, partial x e by partial x prime a, gamma c d e. Okay? Then there is a multiplication term, that partial x prime j, partial x f and u f. Okay? Samajh aaya? Now on which index there is a sum? The j is a summed over index. Clear? Samajh aaya? Now look here, you are having a term which contains this thing, and you are having a term which contains j in the upper case. Clear? So everybody agrees it? So when you sum over j, so these two terms will give me what? Delta df. Clear? Now you sum over f or you sum over d, okay, because there is an f as well, there is a d as well, you sum over f, let's say. So f will be replaced by d. So which implies partial x prime I by partial x c. Then I am having this partial x e by partial x prime a. Okay. Then what you are having? T c d e u d. Okay. समझ आवा? समझ आवा? Okay. Has everybody written this very step? Huh? Okay. Okay. So now I am having the, okay, look at this term. So this term and this term I am having at hand. Okay. So let me rewrite this very term. Okay. So let me erase these terms because they are now cancelled. So this I require. Okay. So this I require this very term. I will keep it in the back. This. Okay. Okay. So let me rewrite it. Now what you are having? You are having the same transformation rule here as here. Do you see? So now what you are having? E is a dummy variable, clear? And D is also a dummy variable. Let me put it in this fashion. So let's write, okay, C is also a dummy variable, is it? So let me write this C. Can you tell me how I should put it? When you say. So let's interchange C. Okay, so let me write it partial x prime I by partial x d, clear? Then, okay, so let me write, I have interchanged this C and D, okay? Then I will write this partial x c is replaced by d, then you are having this partial x prime A, okay? E I will replace by C. So then you are having D, okay? Yes? When you say? Huh? So D is here, then C is here. So what remains? E, clear? So how to put it? इसमें क्या indices याद? Huh? Yes, it's okay. There is no problem. There is no problem. Let's write here F. Then you are having UF. Okay? समझ आवा? So this D I have replaced by F. Huh? Okay? So I have made sure this object comes here. Okay? So therefore, so what you are having, okay, that partial prime, what is here? What we wrote here? A. What was here? A. Then UI plus gamma I. Then JA UJ. Is that true? Is this what we have written? So just be careful with the indices. Now let me take these differentials common. So it's partial x prime I by partial x d. Then you are having partial x c by partial x prime a. Now what remains inside? That partial c u d plus gamma d f c u f. समझ everyone? So it is the same thing, partial derivative of u and gamma and u, is it? So what you are having? A well-defined transformation. There is no additional term. समझ everyone? Got it? Now count the free indices on both sides. When you check the, if you need to check the your equation is correct or not, you check the free indices on both sides. So what are the free indices? I, A, is it? So two indices are here free, and you have to be, those indices need to be here. You are having I and A. I is up, A is down. I is up, A is down. Clear? All the other indices are contracted. समझ everyone? So in other words, this object transforms as a rank 2 tensor. समझ आवा? You got my point. So in other words, so what was our this point? Okay, so we had this very object UA, okay, partial A, then UI plus gamma I JA UJ is equal to 0. So it means this very object okay, transforms as a rank 2 tensor, mixed tensor, because one is up and another is down. Okay, so let me define an object. So if you see, this is actually the generalization of a derivative. So because it contains a partial derivative plus some additional terms. The additional term, if you see, this gamma contains the metric tensor. You can see it is related to the curvature of the space time, or it is related to the curvature of a given space, curved space. So, because this we told in the previous lecture, so we were we said that this G represents the intrinsic curvature of a manifold or intrinsic curvature of a given surface. So that means this gamma is related to the curvature. So when you are having a flat space time, then this gamma is equal to 0, you return back this very term. So in other words, this object is actually a generalization of a partial derivative. Okay, and this partial derivative is invariant under coordinate transformation. Any general coordinate transformation, this is invariant. Okay, so okay, so what does that mean? If it is an invariant under coordinate transformation, we call this derivative as a covariant derivative. So let's define a derivative. So like this thing. So we call ui. So it's like this thing. So the partial derivative plus the affine coefficients are the Christoffel symbols, J A U G. So defines covariant derivative. So when this is invariant under coordinate transformation, it means this equation is invariant. So then we are having equation of motion like this thing, ui, that's equal to 0. So this is an equation in covariant form. Okay, so it is a vector equation. Now A is contracted and it contains only one index, so it will transform as a vector under general coordinate transformation. Got it, everybody? Okay, so now let's, so you can have actually this covariant derivative. So you can act on, so here I have acted this on a contravariant vector, is it? So we can act this on a covariant vector as well, like this thing. So what we have, okay, so let me write covariant derivative what we have at hand. So this is important, okay, so this very important thing. So how we define it? So you define it acting on a vector, without acting on a vector it has no meaning. So you write, let's say some u b. So let me write b here now. So it will be partial a, okay, differentiate simply partial derivative of u, then you write a gamma, is it? What is the upper index? So let me tell how to write. Upper index is b, put the upper index on this gamma, clear? So what is the lower index? A, so you put it on here, then put a contracted index, let's say f, so uf. Got it? So you write some velocity vector here and then put an index which gets contracted. You can write c, no problem. Okay, so this is on a on a covariant vector. Let's say ub, how it acts. So I am having like this thing. So you can show, okay, try this exercise at your places. Okay, try this at your places, how it will act. Okay, so it acts like this thing, partial a, the derivative the same way, no problem, then minus, write this gamma. Now you are having here a plus, and for the contravariant vector here it will be a minus. Okay, so you are having ub, what is, both are lower indices, is it? So in this case one was the upper index you put at the top of this gamma, Now you are having both are lower indices, you put where? Here. So you put first B, this were index first, then this index, clear? Okay, then write a velocity vector. Now you need a index which gets contracted. Let's write that here. समझ आया? So this is a way how to write it. Clear? Okay. So similarly, we write actually covariant derivative of a scalar is simple partial derivative. Huh? Okay. So let me write covariant derivative of a scalar. So partial a phi, that is same as what? Partial a phi. Okay. So let me put it this, instead of proving this very result, it is a trivial result. So phi is a scalar quantity, is it? So that means this is actually the gradient of phi. Gradient of phi transforms as a covector, clear? So that means this is a vector itself. That's why you don't need the affine connections in for the scalar quantity. समझ आया? Okay, so the covariant derivative of a scalar is same as the partial derivative of the scalar. Now covariant derivative of a vector is these things. Now let's write a rank 2 tensor. Then it will generalize how to write the covariant derivative of all these things. So I will give you the outline. So let me write you are having a rank 2 tensor. So let's say TAB, it's a rank 2 tensor. Okay, or it may have as many upper indices as lower indices. Okay, you can be having many upper indices as well as lower indices. Okay, I will give you the prescription how to write it. Okay, so you can prove it. There is no problem. You can write it. There is a well-defined formula of writing the covariant derivative in general. We have arrived at a covariant derivative in a different perspective, but there is a definition, the first principle definition of the covariant derivative. Okay, so those things I have not touched. I have just given you an overview what a covariant derivative means. Okay, so let's write it. Let me write it as covariant derivative of this tensor. Okay. समझ आया? So now how to put it? For the time being, okay, now look here. If you see, you are having, when you write covariant derivative of upper index or lower index, both contains what? This partial derivative. Okay. So that means whenever I will act covariant derivative on any quantity, there will be actually a partial derivative. समझ आया? So that means first step you have to write the partial derivative of whatever the quantity here is. Okay. So let's write TAB. First step is covariant derivative means what? A partial derivative. Then I need to put all these affine coefficients, these gammas. समझ आया? Are these Christoffel symbols I need to put? So how to do that? So forget about this index B for the time being. Okay? So let's forget it. So if I forget this B for the time being, okay, so what I will write? Look at that very formula. So I need to put a gamma, a plus sign gamma. So upper index here, then, so let's write some F, okay, I, then this T, is it? What is having the index? It should be having index F, but you are having here what? An index B, so that index you put here. समझ आया? Got it? For the one index I have put it. Now let's do it for the, forget about upper index. When you forget about the upper index, okay, for the moment let's forget about this upper index, clear? समझ आया? Okay, so let me write it for the time being. Okay, so let me write it here for here. So I will forget about the upper index, clear? So that means I am having only a lower index. Okay, so for the lower index what I need to put? This kind of object. So let's write gamma, then you are having BI. Okay, so let's write F, then you, okay, so then you are having this T, so F, clear? So what you are having here? An upper index. So that means whatever index you are having, you put this gamma factor in that way. समझ आया? This term will be same. So partial derivative of that very term and the gamma factors defined for upper and lower indices, clear? Now let's say if you are having more indices here, let's say if you are having gamma I, T, A, B, C, let's say J, K, L. समझ आया? Try this. Got it? For each, okay, first you will put a partial derivative, then you have to adjust what? These gamma factors. You say there is only one index I, then there is index j, or then there is index a, b, c, whatsoever. So for each index you put a gamma factor. Clear? Try this very factor. Okay, got it? Okay. Now let's go to one of the important things. Okay, so last time somebody asked me the question, suppose if I don't know the metric, or if I don't know what is the nature of the space time, how I can say it's actually the curved. Okay, it's a curved manifold. So there is actually the general prescription. Okay, if there is a kind of tensor which actually gives you the which purely constructs the geometry of a given space time. Or in other words, which gives you the idea of a curvature of a given space time. Although that kind of quantity is related to the metric tensor. Fundamental quantity is the metric tensor, okay, but it will come through the derivatives. We will see that kind of thing. Okay, think of a sphere. Let's say what I mean to say. Okay, so let's think of a sphere or surface of a sphere. You displace, let's say, a vector. Let me make this kind of object. Let's say you start acting a covariant derivative. You displace a vector in this very direction, then in this very direction. Okay, and then you move from here to here. Okay, you move along this kind of path and move along this kind of path. If you look at the flat space geometry, it doesn't matter. So the vector will remain always the same. The direction will remain always the same thing. Or in other words, if you carry an operation, let's say if you make a derivative acting in this direction, then a derivative along this direction, and then you do the other way around. You perform the x derivative first, let's say this kind of derivative first, then this derivative as a second. So you will see in the flat space time it will be 0, because if what I mean by that, let's apply the partial d by dx first, then apply d by dy. Okay, that means along x direction and along y direction. So it is the same thing if you apply first y direction, then and along the x direction. D by d2 d by dx acting on d by dy is same as d by dy acting on d by dx. Clear? So that means that this commutative of these two derivatives says the underlying geometry is actually flat. Now a derivative that is defined on a curved space time, that is our covariant derivative. Clear? It is a generalization of a partial derivative. So that means if I take a commutator of two partial derivatives or these covariant derivatives, okay, so that should give me actually the measure of what? Curvature of the underlying space or the underlying space time. Now look, okay, so again let me take the two partial derivatives x and y. Those are the same thing whether you take first x or y or x. Clear? So they are commutative. That means the underlying geometry is what? Flat. Now let me take the two covariant derivatives, or in other words, let's say if these two derivatives do not commute, what does it mean? So the geometry is not flat. Because the action of the derivatives will act on will depend on a given trajectory. Is that true? Let's say if you act a derivative, let's say like this thing, you act a derivative d by dx, d by dy. Okay, then you act a d by dy and you act what? D by dx. Let's say if they are not the same, this acting on this thing, let's say acting on some function, if you go along this direction and then go along this direction, okay, if these two results are not the same, what does it mean? So this action of the derivatives depends on a given trajectory, is it? It depends on the path taken. So when it depends on a given path, so it means it defines your geometry, is it? Now if they commute, if they are the same thing, that means what? They are independent of the path. It means the underlying geometry turns out to be what? Flat. So now let's go to action of these covariant derivatives. This is simple idea to understand. We can do it in the other way around, but I will not go that details. Okay, any question? So let's take, so this will be actually a large commutator. So commutator does not mean you are doing the quantum mechanics, okay? समझ आओ? It does not mean you are doing quantum mechanics. So it means, let's say I am having okay, partial j acting on some vector xa, the covariant derivative, then I will act some this delta I, okay. So then I subtract like this. So let's check the result of this thing, okay. तो ये बात समझ? Okay, to simplify this kind, okay, so this is equal to like the commutator acting on this arbitrary vector xa. So let's check what this yield is. So if this is 0, that means our underlying geometry is what? Flat. Okay, if this is not equal to 0, that means I am having a curved space. This will help actually. This commutator defines actually what we call the Riemann curvature tensor. Okay, so we will see it in a moment what exactly it means. So let me take this thing. So let's apply this partial j xa. Okay, so how many indices this object is having? How many indices? Oh, we know. So 2 indices. Let me call this as TAG. So let's define this object like this. Clear? So now operate this thing. So it will be partial j xa plus gamma a. Then you put j. Let's write f xa. Clear? समझ आवा? Okay. So now what I need to do, okay, now look at these two terms. First look at these two terms. You are having ij here, then ji here. So that means in this very term I and j are interchanged. So I need to evaluate only this very term. The result of this very term I can substitute for j and I. समझ है man? Got it? Okay, so we need to calculate only this very term. So therefore I can write this partial I, this, okay, sorry, delta j xa, this object. Clear? Let's operate. What this object I have written as? TAJ. So this is simple thing to do, to avoid the confusion between the indices. So I will write it as TAJ. Then we will substitute the value of this TAJ, that is this object. Samajh? This is simply to avoid the confusion in the indices. Okay, so now this is a tensor, is it, of rank 2. So I need to activate this covariant derivative. What it will be? Partial I TAJ. Then I will be having this gamma. Forget about this j I. So let's write f t f. Then when you say j. Clear? Samajh? Then forget about the upper index a. Then it will be gamma. Let's write f. So when you say j I, then you are having this t a f. Okay, समझ आओ? Now let's substitute for this t. Okay, so be careful. So we will substitute for this t. Okay, so let's call this as 1, call this as 2, call this as 3, using second and third. Okay, so which implies, okay, so what it gives me? So it's nebula I, nebula j, xa. So how much is that? Partial I. So what is ta? Okay, so look at carefully the indices. What the index you are having? Just be careful. You are having ta j. This is actually a general this ta j, is it? Now look at this. What is the index? F and j. So that means these upper indices you have to replace by f. Clear? So by the way, f is already a contracted index. Let me write here instead of f. So let's write c. So let's write c. So let's write c. So let's write this as c. Okay? A B C. Okay. S was like on B. That's it. So what is T I? T A J. Tell me, TAJ is this object. So it is partial J XA plus TAFJ XF. So it is the first term. Then you are having plus gamma A CI. So now tell me, what is this thing? What is TCJ? That means T is like this thing. J is there. J has nothing to do with, only the upper index is changed. It is C. So it will partial J XC plus gamma C, okay, FJ XF. Okay. Then you are having minus gamma C, okay, J I. So what you are having, TAC, lower index is changed. Is it? A is there. So it is partial C XA, then plus partial A F C XF. Everybody, because this is C, so J will be replaced by C. Okay? Any problem? Okay. So let me simplify this a bit. So this means partial I, partial J XA plus so this is a derivative, these are two terms, is it? So that means you have to act, you have to make a product rule, okay? So it's partial I gamma A Fj XF, then you are having plus gamma A Fj partial I XF, okay? So these two terms come from here, okay, acting the derivative. Then you are having plus gamma A Ci partial J Xc plus gamma A Ci gamma C Fj XF, okay. And then you are having this minus Kharesha, minus this very term gamma C Ji partial C XA, then you are having minus gamma C Ji, just I am multiplying things, XF, okay, clear? Okay, so let us call this as fourth. So now this is which term? Delta I, delta J, XA, clear? So I will interchange I and J, okay. So which implies therefore this delta I, delta J, delta I, so it is the next term. So it means you need to actually interchange what? I and J. So that means in this very term you interchange I and J. So what you will get? So partial J and partial I XA. Then you are having partial, this I will be replaced by J, gamma A F J will be replaced by I. Then you are having this XF. Then you are having this gamma A F J is I partial J XF. Okay. Then you are having this objective gamma A C I will be replaced by J I, okay, like this thing, plus gamma A C I is replaced by J, J is replaced by I XF. Then you are having minus gamma C I J partial C XA minus this gamma C. So this will be again I J gamma E F C XF. So call this as equation 5th. Okay. So now let us take the subtraction. Okay. So subtract the two, which implies gamma I gamma J minus gamma J, delta I delta J minus, okay. So like this thing. Now look at these things. So when you subtract, okay, so be careful, huh? So when you subtract, you need, so this will be minus, 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 so this will be plus, this will be plus. So I will not write all the terms. Now look here. So you are having partial I, these are the partial derivatives, clear? Partial derivatives are commutative. This partial I, partial J is same as what? Partial J, partial I. So that means this very term will cancel. So let me write this term cancels with this very term, okay. Now let us look at this very term. So let us keep these as such. Now let us look at this term, Okay, so you are having partial I xf. Where is partial I xf? Anybody? So you are having f. Okay, look at this very term and this very term. So you are having partial I x, is it? Partial I x, j is here, is it? So c is a dummy variable. Is c a dummy variable? F is also a. So you can replace the c by f or f by c. So that means this very term cancels. So I am making these different signs so that you will understand which term gets cancelled with which term. Okay. Okay. So now let's look at this very term. Okay. These two terms. So you are having I here, j here, gamma a. So f is a dummy variable, c is a dummy variable. Clear? So this is a minus and that is minus. So this cancels. This cancels with this very term. Okay. So now let's look at the other terms. These two terms. So look here. At this very term. So you are having gamma c ji partial c xa. Partial c xa is there. Gamma c is there. So since we know gamma ij is same as what? Gamma ji. So this very term, since it contains a plus sign, okay. So when you take a subtraction, it will be plus. So this term cancels with this very term. Samajh aaya? So these two terms cancel. Okay. So how many terms are remaining? Now tell me. So there are, okay. So these two terms, okay. No, there will be 4 terms. These two terms, okay. Then you are having these two terms and these two terms. Okay, so let's look at which term. So there will be one more term which is cancelling. Yes, this term is cancelling. So let's look at this very term. Put in the rectangular box. This is with a minus sign. This is with what? Plus sign. So this term cancels. Why? So you are having fc xf gamma a. ij is same as ji. So what we have used? This gamma, let's say aij is same as gamma a ji. Okay. So this we have already assumed to be symmetric. Okay. There is, okay, when you are having a space time where these affine coefficients or Christoffel symbols are symmetric in the lower indices, we call those as torsion free space times. Okay. There is no torsion. Okay. So this is a very important thing. So although our analysis says gamma ij is same as gamma ji. Okay. So let's forget about what torsion means. Forget those terms. Okay, because we will not be doing torsion anywhere in our theory. Okay. So let's write what are the remaining terms. So it's partial I gamma a fg. Okay. Now look here. Each term is having what? xf. Clear? xf is multiplying each term. So I will take xf out. So let's write partial I, this object minus. So I will tell you how to memorize this thing. Okay. Then you are having the gamma term with a plus sign, gamma a ci gamma c fj, this very term. And then you are having this term minus gamma a cj gamma c fi. So each is multiplying this x. Now look here in this very commutator. Now remember this very term. So these two terms are anti-symmetric with each other. So f is a dummy variable, is it? Forget about the upper index. What are the indices? I and j. So what you are having? J and I. So if you write this kind of term, just interchange I and j with a minus sign. Is it? So j and I are replaced in this very case. So but you are having a minus sign. Look at this term. You are having gamma and gamma. Put upper index and then contract with the indices. Okay. So what you are having? I and j. Look at this. J and I. So it's an antisymmetric term. So this I can define this commutator. So these terms are non-zero. In general, they are non-zero. Okay. So now look here. If you see, this gamma contains essentially the derivative of the metric tensor. Clear? So now you are having again the derivative of what? The gamma. So that means it is a double derivative of a metric tensor. Now if you remember, when we are doing the local inertial coordinate, so we said the first derivative of the gamma should vanish, is it? So that to define the what? the local inertia, but the higher derivatives we do not guarantee whether they are 0 or not. So that means the curvature comes from where? The higher derivatives of this metric tensor. Okay, so that's why you can say you are having here actually a double derivative of the metric tensor. समझ आया? So this I can write. Now tell me, forget about that xf. How many indices you are having? Upper index is 1. So lower index are I, F, J. Then I can write this xf. So this R we call as a Riemann curvature tensor. It's a rank 4 tensor. Okay. So now let me define. So that means if the Riemann, okay, so now there is a theorem, if you are having a flat space time, so the Riemann curvature tensor must vanish. Okay, so let me put, so let me write first this Riemann curvature tensor, then I will write the statement of a theorem. So we define this Riemann curvature tensor as R A I F J. So this I can write as, so let me write instead of F, so let me write, you can put K as well, there isn't any. Let me write I K J, let's write this way, R, so B C D. Okay, so let me write this thing, so that you will remember things. So now look here, look at this very thing. So F, the middle index I have put as a contracted index, clear? So that means the middle index you put at these things. So you have to only do things with this I and J. समझ आया? Forget about this middle index. So what I will write? So I will put a partial B, then I am having gamma, so A is there. Okay, so then you will write this D. Okay, forget about this index for the time being. Okay, then you need to interchange this B and D, so it will be D gamma A, so write B. So you can put now here C. Okay, then you are having the another thing. Okay, so the multiplication of these gammas, you write first gamma as gamma A, then write the second gamma. Okay, so in the first case, okay, the first gamma, so let's write some index F which is contracted with this gamma. Okay, then how many indices are at hand? 3 indices, is it? Lower indices are 3. Okay, so you put one index where? So let's write one index B here, then you put the other 2 index C, D here. समझ आया? The second thing, the second 2 indices you put on the second gamma. Then if you are able to write this very term, then make the interchange of first and the last index B and D. So it's A gamma F, so it will be as such F D C B. Okay, so this is the Riemann curvature tensor. Now we define, okay, which is very important. Okay, so I will not go to the symmetries of this very thing because we will not be using it. Okay, so this actually from here we have to get actually the idea of what we call the Ricci tensor. So we define this Ricci tensor. So if I contract the 2 indices of this very tensor like this thing, let's contract this upper index and the middle index. Okay, so let's contract the 2. So if I write like this thing A B A D, so this is a contraction. That means you put 2 indices same. समझ आया? So how many indices are remaining? 2. So this is a Ricci tensor R B D. So this is a Ricci tensor. One index is contracted. Okay, it means there is a sum over this A, or in other words you take trace over the index A. समझ आया? Okay, so this you can also write as, okay, so can anyone tell me in terms of the metric tensor how I can write it? Raising and lowering index? Huh? Okay, so let us define now what we call the Ricci scalar. So I need actually G, and you multiply like A, B, C, D. Okay, समझ आया? What kind of indices you need to put on G? Huh? What is it? Where? Yes, C upper, E lower. Clear? So that means A is replaced by Isha. So this is how you can do it. Now let's write the Ricci scalar. So that's R is equal to. So look here. So this is actually the curvature tensor we will be interested in. A Ricci tensor describes actually the curvature of the this pseudo Riemannian manifold or the space-time geometry. We will be interested in this very object because it is a rank 2 tensor. Now there is a scalar quantity what we call a Ricci scalar. This also defines the curvature, but a scalar curvature. समझ शेवन? Okay, so if I write now this as GBD RBD, so that means you are contracting both the indices. So it defines your Ricci scalar. Okay? मैं लिखा ये ठीक है ना? GCA RABCD. Can I write it? Can I write it? So I can put it this way. You put this index here and keep this above. Okay? Got it? Okay. What we have now, there is an idea. Okay. Now our curvature. Okay. So let me. Okay. Let's forget about all the mathematics what we have done. Clear? Samuchaman. So let's go to the Einstein's idea. So then we will go to its solution. Einstein's idea is that the curvature of this given space time produce actually the gravity, is it? Or in other words, the mass, okay, if you are having a mass at a given point, it affects the curvature of that space time. Samajh? Or in other words, the gravity is generated by what? Curvature of the space time around a massive object, any particle which carries a mass or the energy, I should say. So that means if I am having a curvature, it should be actually proportional to some quantity which represents the what? The energy density. Samajh? This energy density, it should also carry the momentum, it should also carry the flux. Samajh? So there is a quantity what we call the energy momentum tensor, which has inbuilt everything. It is the energy density, it carries the momentum, other terms are the fluxes, is it? Samajh? Or in other words, it carries the Poynting vector, if you remember from the electromagnetic field. Okay? So I can say then the curvature must be proportional to what? The energy momentum tensor. Samajh? Okay. So let me define the Einstein tensor first. So Einstein tensor is like this thing. Let me write this GAB. So it is the Ricci's tensor minus half of GAB Ricci scalar. Okay, because this is a scalar quantity. GAB is a tensor, this is also a tensor. So what Einstein said, this GAB must be proportional to what? The energy momentum tensor, TAB. Samajh aaya? So this TAB is what? Energy momentum. Okay, so I will argue, we will take it in the next lecture, no issues. So what is our this thing? So or in other words, I am having RAB minus half of GABR. So that's equal to K times this TAB. So this is the Einstein's field equation. So it was actually an intuitive guess. So later on, people try to figure out what is actually an action that will describe this kind of equation. It was actually the Hilbert, okay, who figured out actually a well-defined action to get from the variational principle this kind of equation. Okay. So this K is equal to, it is something 8 pi G. G is the Newton's constant by C raised power 4 TAB. Okay. So we will put this equation on more footing in the next lecture. Okay. So for the time being, this tensorial mathematics is gone. Now we have to do the simple mathematics. Okay.